He says so.
Good morning, everybody. So my name is Ayomide, and I'll be working on teapot effect. I'm presenting today with my colleagues. Two of them, they're online, so I'm the only one here today in presence. For tea lovers, if you observe that when you're trying to take some tea in the morning or in the afternoon when you're tired or something like that, you notice something around the spout of the kettle, and you notice that the tea that is coming out of the spout of the kettle, it clings to the spout of the kettle. And what do you think might be the reason for that? And that's what we're trying to explore today using fluid mechanics principle. So there are several theories that have been propounded to support this effect. And some of these theories revolves around surface tension, around internal vortices, around air pressure differences, and around the capillarity effect. So for the surface tension, we all know that surface tension is just that effect that makes the surface of a material to feel like it is being layered by elastic membrane. And what happens here is that when tea is being poured out of the kettle, especially if the kettle has a narrow spout, what happens is that due to adhesion and cohesive forces, the tea clings to the tip of the kettle, and that is because of surface tension. And also for the internal vortices, what happens is that when we're trying to pour the tea out of the kettle, what we experience is that we experience this swirling, or let me say this swirling current, and this swirling current causes the tea to climb the spout down. And this causes, especially when you are drinking on the table, on a white table, you notice that the tea has been layered on the table, and that's because of that. We have the air pressure differences as well. If the spout is narrow, what happens is,
Drinking on a white table?
like you place your cup on the white table, you notice that the tea spills on the table. It spills on the table, especially when you're using the kettle, because everything that is coming out of the kettle is not going into the cup. Some of them come out on the tea, on the table, and it's because of these internal vortices, the swirling current. So for the air pressure differences, what happens is that when the tea is coming out of kettle, especially if the tip of the kettle is narrow, as I said, the liquid causes the air to be trapped out from the kettle, and it causes a temporary differences in the pressure, in the air pressure between the kettle, inside of the kettle and outside of the kettle. The capillary effect is, we all know what is capillary, and so that's it. So this is just a video that explains this better. All right, so this is what I'm talking about. You notice because of the narrow spout and because of this kind of shape, it causes the water to be flowing down, So that's what I'm talking about.
Try one more time and walk us through it.
Okay, cool. Let me try it again. All right, so because of the narrow spout and because of the slant shape, the tea is coming out of the kettle, and as the tea is coming out of the kettle, you notice at medium flow rate, it's flowing very well. It's fine. It's not having the clinging effect. So when we have very low flow rate, what happens is that it clings to the tip of the spout of the kettle, as I explained in the beginning.
So no matter how fast you pour it, in the end you got to pour it slowly because you're going to turn it back up, so you're going to spill something, right?
Not really. It is the flow rate, the rate at which you are trying to pour the tea out of the kettle that matters.
Yeah, but eventually you got to slow it down, right?
That is when you are trying to bring the kettle back to the table.
Yeah.
Oh yeah, definitely. Yes.
Our project will focus on research.
All right, so this is a recording of the other part. Is it playing?
It started. Maybe try one more time. Yeah, push the play button.
Done by Sechel and his group called Developed Liquid Film Passing a Smooth and Wedge-Shaped Trailing Edge, a small-scale analysis of the teapot effect at large Reynolds numbers. The Cetral paper concentrates
What's happening here?
on the region close to the end of the spout where the flow separates from the pot surface. This figure shows that the region near the end of the spout is divided into half a dozen nested regions, with each region having different conditions. The innermost region is actually so small that the curvature of the spout is ignored and the lip can be regarded as a flat surface and unbounded in width. The flow in each region influences what happens in neighboring regions, making the mathematical modeling of the flow very complex. The authors can solve simplified versions of the Navier-Stokes equations in the key regions near the end of the spout, which show that inertia, capillarity, surface tension, and viscosity all play a role. The Cetral paper assumes fully developed flow, so it doesn't look at the starting or stopping of the pouring process. Since the detachment point is where the fluid goes from no slip to free slip, this requires looking at very small length scales. The paper also assumes large Reynolds numbers, which indicates the energy of the flow motion dominates the dissipating effects of viscosity. The paper non-dimensionalizes its equations based on a slenderness parameter, which is the reciprocal of the Reynolds number. The Weber number is also a key parameter, and it's a measure of the fluid's inertia to capillarity or surface tension. For high Reynolds numbers and Weber numbers, inertial effects overcome viscous effects and capillary action. Since water isn't a very viscous fluid, it's easy to have a high Reynolds number, but water does have a high surface tension, which is why the teapot effect is so prominent. Capillary action occurs when the adhesion of water to the teapot is stronger than the adhesion of water molecules to each other. Surface tension holds the fluid surface together, which causes water to tend to dribble down the side of the spout. The paper looks at various regions leading up to the actual detachment point. It develops a model that shows how the detachment point changes with Reynolds number and the angle of the spout beta. The distance d from the apex decreases with both increasing values of beta and Reynolds number. Surprisingly, gravity is relatively unimportant in determining whether drops form or not in the teapot effect, although it does affect the direction of the poured arc of fluid in any falling drops. Not shown in this equation is the effect of adhesion of the water to the surface. As a rule of thumb, the higher the wettability, the more the fluid sticks to the underside, and the further the detachment point is from the plane wall on top. Another paper by Duez and his research group show that using a super hydrophobic substrate eliminates water adhesion to the teapot, eliminating the teapot effect. There's a demo at the end of this presentation that shows this in effect.
Based on the findings in the previous slide, there are three design variables to prevent or reduce drop formation: the speed of flow or the speed of pouring, the sharpness of the spout, and the wettability of the teapot surface. For design variable 1, speed of pouring, the potter can design and make a teapot in such a way as to make pouring as easy as possible, so that the fast midstream flow is quickly and easily achieved. Small light teapots with an easy-to-use handle and a flat profile handle with room for multiple fingers to allow a firm grip will help you achieve this. A relatively long spout will also help you achieve this, as it is easier to pour tea quickly at a steep angle. The steep angle ensures flow has enough inertia to detach from the spout. There are several spout design requirements to help prevent drop formation. The spout should be long to enable fast flow. The spout should be designed with a sharply cut-away lower lip and should be as thin as possible while maintaining strength and durability. In the graphics in the slide, the gray triangle represents the tip of a spout with various internal and external angles selected by the lip-shaped button. The blue line is a thin layer of liquid flowing on the surface, with the ideal case being that it falls vertically from the tip of the spout. Comparing the images on the left to the images on the right, you will see how the flow on the surface changes with the lip shape remaining constant and flow rate changing from slow to high. Comparing the images on the top to the images on the bottom, you will see how the flow on the surface changes with the flow rate remaining constant and lip shape changing from flat to high. Some potential designs that have not been proven include adding bends or flaring to the spout, reducing the spout diameter, or adding ridges or grooves to the underedge. From a fluid mechanics viewpoint, some of these suggestions could prove advantageous, however many of them could interrupt the establishment of smooth flow at the end of the spout, which could lead to turbulence. The third design variable to reduce drop formation is wettability. Most ceramic teapots are glazed, typically a full gloss versus a matte glaze, so options are limited here. The way to change wettability is to coat the lip with a hydrophobic material. This comes from the old idea of smearing butter on the spout to stop dribbling. The butter repels water and prevents tea from clinging to the teapot. The images on this slide illustrate the change of wettability of the surface and how that flow changes. Comparing the image on the top to the image on the bottom, you will see the flow on the surface changes with the material wettability changing from low to high.
All right, so we have, to prevent this, we have 3 anti-drop solutions for preventing the clinging of the tea to the spout. So the first one is the spout insert, and the second one is the drip catches. Then the third one, I'm going to explain that. So for the first one, is about the spout insert. What they're going to do here is they're going to fix this material. They're going to place it inside this the spout of the kettle. And so when you're trying to pour, it reduces or eliminates the clinging effect that we normally experience in the other parts without using this. And so for the second one is for the drip catchers. So what drip catchers does is that when you are trying to pour, it's the property of this material, the rubbery property of this material prevents the liquid. Sorry. The property of this, it prevents the liquid, or let me say the tea, from clinging to the tip, and it helps it to flow properly the way we want it to be. And so the third option is the use of butter. So we use this butter. You can layer or you can glaze the material, the kettle, with butter. And what this does is, because of its hydrophobic property, it helps the tea to flow in the way we want it to be. So for instance, let me show you a demo of when we use the kettle without the butter. You see, at the end, the water, the tea is coming back, it's clinging to the tip. So when we use butter, when we layer the kettle with butter, let's see the effect. It reduces significantly. And so when we use a good design, that is kettle with narrow spout and long, the spout is narrow and long, let's see the effect as well. If you observe at the end of that video, it even seems to the extent that the water is trying to go back into the kettle. That shows the effect of using a very long spout with narrow mouth. Thank you. Thank you very much for the presentation.
Questions from the audience? So the teapot is related to the surface texture of the liquid. So you said that the water has a high viscous effect or like surface tension. That's why there is a teapot effect. Is that the reason why we always get like honey on the jars?
Oh yeah, true. Because when you have high surface tension, what happens is that it increases. We all know what is surface tension. The effect of surface tension is to make the surface to look like though it is being layered by elastic material. So This elastic materials causes the water to be sticking to the surface of the material instead of it to allow it to flow properly. So, but if you observe in butter, which is not elastic material per se, it is hydrophobic in nature. It allows the flow of the tea to go smoothly as we expect it to be. Do I answer your question? Thank you.
Go back to that video, the last video.
The last video,
The good design.
the good design.
Why don't they just all make it? Why don't they, like, basically it's U-shaped, so the fluid has to go up against gravity and then go back down again. Why aren't they just all design? Why don't they just all design it like that? Like, why is that not more common?
Oh, wow, that's a nice question. I don't know. I think maybe it depends on the designers. I'm not too sure why the designers, some of them, maybe because that one might look better, or I don't know. I don't know why designers do that. But let me see. Maybe my friend can be able to support. They have a support. And so, do you have any solution to this?
Yeah, can you hear me?
Okay, cool.
Right. Honestly, I think a lot of people have to aesthetics. I think it would look kind of silly to want to have a U-shaped pot. Kind of the reason why a lot of people in the market, like, people buy it and it looks pretty, so you don't necessarily test how well it pours water in the store. And so, yeah, I mean, it would probably be very nice if it was very nice, but it would just not be aesthetically pleasing to a lot of people, so it would sell.
There's also manufacturing costs involved in that. It's extra steps. Just a thought.
Thank you for that.
You could even continue it even more. Like, when you pour that one, you could make even like more U-shaped, so it'd have to like go back up.
Yeah, exactly.
But I guess that
It's more expensive.
you can lose respect of your tea drinker. Yeah, like that one on the left that doesn't work very well. Yeah.
It does look a lot like an elephant trunk, doesn't it?
Go to the there's that image of all the 12 different regions.
I'm coming.
Oh wait, actually go back to
There's
the one with the
third design variable to reduce drop formation.
This one. Okay.
I don't understand tell us how the insert works.
Well, so for me, I think because of the inserts, they are hydrophobic materials as well, like butter. So what it does is that it
It looks like metal. I don't think it's hydrophobic, is it?
is.
Oh really?
Yeah, it is.
Coated with hydrophobic
Yeah, it is. It is hydrophobic. So it's, it prevents the clinching effect because it reduces the viscosity that lets the water or the tea to clinch to the spout, as the same effect that the butter has. But we observe that the one with the butter is even more better than this. I don't know why, but maybe because butter is more, more hydrophobic in nature than this material. So that's what I can say as regards to design.
And the bottom ones, they also just need the fluid to go back up to spill, right?
Yeah, yes, exactly.
Yeah, but those look terrible.
Yeah, it's not looking good. So this one is not functioning like this one. This one is just to prevent. This is the normal kettle. The only thing is that this absorbs the water from going back. So yeah.
Okay, now go to those regions. I didn't exactly
Third
understand what's
design
going on
variable
here.
to reduce drop
These are-
formation is
That fluid coming
wettability.
out of that's the
Most
teapot
ceramic
spout?
teapots are glazed,
Yeah, this is the
typically
spout.
a full
This is the
gloss
spout.
versus a matte glaze, so options are limited here.
This will be the last
The way to
question.
There are several spout design
This one?
requirements
Oh.
to help
12 regions.
for design.
Which of them?
The sisal paper assumes fully. The sisal paper concentrates on the region close to the end of the spout where the flow separates from the pot surface. This figure shows that the region near
Turn
the
off the
end of the
sound.
spout is divided into half a dozen nested regions.
So you said you have different dimensionless groups in each of these regions or something? Like, what's the difference between MD and LD?
No, Antu. Antu, can you listen?
What's actually what the paper did is it focused on that green region. MD stands for main deck, LD stands for lower deck, and so they had essentially
Okay. So for your course project presentation, you guys will talk about you saw there's this experiment, they pour tea underwater and you still get the teapot effect, right? And two, basically they have colored tea under a swimming pool and you pour it, well, heavy, you had to make it like salty. And I think you still get the teapot effect.
Wow.
Okay, that could be something that we try to do again.
Cool.
Yeah, but I think that Keller paper, the one they just said, this is related to what's called the Coanda effect. When you basically have fluid going past a solid boundary, you're basically going to get some forces due to the fact that you're entraining, like anytime, like if you blow or have a jet, it entrains flow around it. And if you entrain enough flow, you're going to feel your boundaries, and they're going to get influenced by the boundaries. So so basically the fact that no matter what spout you have, you're going to get a little bit of that. But I think that's not based on energetics. That's based on this entrainment of flow. But if you can look into that, that would be really good for the presentation, because that'll be non-overlapping with what you have here.
Thank you.
All right, good. Good job.
Thank you.
Yeah, let's clap. All right. So the people that just came online waiting patiently, yeah, we're like 30 minutes into class now. I was talking about the quiz. So quiz 2 will be on Monday next week. I think the online people, you'll pretty much have the 24 hours to take that quiz. If you need more time, we can talk about it. Oh yeah. Hey, Mitty, you took my microphone. You're wearing it.
Sorry.
So the quiz will be next week. I've written it already. Basically, 2 questions. I was telling my kids, like, yeah, I only give 2 questions on my quizzes, but one of them has like 12 parts. Like, nah.
Thanks for that.
2 questions. One will be on index notation, like quiz 1, and the other one will be Cartesian coordinate startup flow. So remember to practice your basically transient plus the steady state solution. Let's just spell it out. And remember, for the steady solution, you have to solve an eigenvalue problem. And use the boundary conditions. Use BC to solve for the coefficients. Boundary problem, and this is a separation of variables. Use BC to solve for the coefficients. And also understand how to do the work at the surface. Work at the surface, for example, in the last homework, the tiers of wine. And also dissipation. It's funny, I wrote 2 questions, but I wrote you 10 things on this side. Yeah?
Will we have to write out each case and then which case is the eigenvalue, or will that be just stated? Like when we did the class problem, you stated which one was that?
Sure, just a
You basically remember, use an eigenvalue condition. We use the orthogonality of the Bessel function solutions for your homework.
No, I mean, because when you did the example, you just said it has to be negative. How the right-hand side is negative to yield the solution. Do we have to, on the quiz, we have to say like eigenvalue, if the lambda is greater than 0.
Oh, you mean do I have to go into that much detail? No, I think that I just did that for pedagogical purposes. These transit solutions have to die down. So I don't think we need to go into detail that it's got to be like you have exponential functions that are negative powers. I don't think I need to go into that much detail. But I'll also say this will be easier than the homework and easier than the ones that we did in class.
Another question.
Yeah.
Is it going to be open notes or no?
Nah. Okay. The problem with open notes is that I don't want to have to. I think I want to just give one problem that's reasonable, and I can write stuff on the board. But the problem with open notes is that I have to make the quiz like a lot harder, and I don't want to make it harder. I think this is reasonable. This is a reasonable level because I've given you like exactly what it's going to be: Cartesian coordinate startup flow. So we'll keep it closed notes. Yeah. But I'll write what you need on the board, whoever needs it. All right. All right, so, and the homework, we are pretty much going to finish. We'll make a lot of progress this week. All right. So, let's talk a little bit about what we've been doing. All right, so the last problem on the homework involves potential flows. All right. Let's remind ourselves. So we proved a couple things over the last week. This is just a review. Kelvin's circulation theorem basically says if there's no viscosity and the density is constant, the gravity is conservative. So a conservative vector field just means that it can be written as the gradient of a potential. Physically, that means that there's some conservation law, like an energy going on. Basically, if that it's path independent, and like, for example, if I throw an object up, it gets its energy back as it goes back down. Like if you go up the stairs, you get the energy back as you go down the stairs. So this is what it means to be conservative. And basically, we're using this idea that velocity is conservative as well. That we don't care about path, that we want to figure out, for example, this idea of circulation. It doesn't matter what path we take. So Kelvin said, hey, if you have these properties, then basically your circulation doesn't change. You're changing your circulation, which is gamma. And so we talked about circulation before, but let me give you a little bit of intuition for it. So the aeroastro people care a lot about circulation. So circulation has a units of basically velocity times a length. Okay, and and the circulation is the integrator of a certain path. So for example, let's say we have just like a circular flow, like your vortex, and we have this velocity field looking like this. So the velocity, let's say it's given by c over r. That's inversely proportional to r. Then the circulation in this case, for example, would just be the product of these two, u across times the perimeter, which would be 2 pi times 2 pi r times u. Let's just do no vectors. And that would just be 2 pi c. So in this case, basically, you imagine you have like you have the circulation, and it doesn't really matter if I take the circulation really close to it or really, really far away. You're going to get the same value. Okay. And as mechanical engineers, you honestly probably don't think about circulation that much. But if you're aeroastro, they teach you that the first thing in class, because there's this idea called lift. There's the idea of the lift force. The lift force is basically the force that's perpendicular to the direction of motion, and we'll show when you do. I think you have to do. You do drag on the cylinder, and then you also do the lift on the cylinder. This lift force is equal to the following expression. Basically proportional to the velocity of the fluid, the density of the fluid, and also the circulation. So that means, those people that are throwing the baseballs, if they put a spin on it, you could get basically some net circulation. And if you throw it faster, you're going to get even more drift. I think this is really important, like pretty much all ball sports, like cricket, soccer, you care about the circulation. And the reason why the aeroastro people care about it so much is because pretty much all of lift, basically to keep their airplanes flying in the air, they have to have circulation. That's what this says. And then if you have its airplane wing, let's say this is a NACA airfoil, you have the flow past a sphere or a cylinder, and it's not very interesting because it's symmetric. You don't have any net circulation. Basically, the flow in this direction is balanced out by the flow when you integrate in the opposite direction. But once you have an airplane wing, it's possible to have a net circulation. For example, you're going to have something like this. This airplane wing provides steric effects, and it forces the fluid to go down to cling to the edge of the wing. So you imagine you take basically a volume around this control volume around this surface. You have stuff going horizontally in, and it's going down on the way out. So you're going to get a lift force because you're causing all those momentum vectors to be pushed down. Imagine someone's a juggler here, and every air molecule you're like throwing it down. Well, the airplane wing is going to go up in response. Physically, imagine I'm taking the circulation around here. They call this downwash. And basically, you imagine the circulation going to be, let's say it'll be downwash W times H, if that downwash had a velocity W and this had a height H. And let's say this had some velocity V, and then you'd basically, if you integrate in this direction, these V's would cancel. So the horizontal components would cancel, but because you're forcing fluid to go downward, you're going to get this downwash. And how much downwash you have tells you how much lift you have and how many people you can put in your airplane. Okay. So in fact, Kelvin, that's pretty much this Kelvin circulation theorem, and this is basically like they call this a line formulation for lift, I think. Line formulation. And it's also why if you watch the wake of an airplane, you'll see vortices shed. If you see the pictures of airplanes behind them, they always have these vortices because you'll have basically circulation if you have lift. All right. So circulation is related to this idea of irrotationality. So basically, then we introduced the idea of being irrotational. We've calculated. So irrotationality means the vorticity, which is the curl of velocity field. And this is a point-by-point level. Like at every point in the velocity field, you can calculate a curl. And if it's irrotational, it means that we basically don't have any vorticity. So irrotational flows have this to be true. So if flow is inviscid and initially irrotational, it remains irrotational for all time. That's what Kelvin circulation theorem tells us, KCT. It says that there's no change in the circulation. Whatever fixed amount of circulation you have is going to be fixed forever if you have no viscosity. Okay. Remember, this is true if mu is equal to 0, which is generally true for high Reynolds number. So the faster you go, the less the circulation is going to change. Now, if it's irrotational, we don't deal with velocity fields. So for irrotational flows, we use the potential. The big idea is that velocity field is a vector. Potential is a scalar. So you can imagine I'll draw this in 2D. You kind of got your 2D velocity fields here. Your x and y. You've got two independent vectors. All that information is contained in the scalar function. Scalar function, which is a function of x and y and z. In some ways, you can imagine if you got a 2D velocity field, your scalar function is like the elevation of a mountain. Imagine we have the Georgia campus, which is unfortunately actually pretty hilly. Actually, I kind of got to start to like it that it's so hilly. But the information on what your velocity is would be basically on how steep you have those hills. For example, right outside the library, you got a big hill up to the stadium. That would tell you, the steeper your potential is, the more velocity or higher magnitude your velocity is going to be. And that's what this tells us. And the reason why we can have this is because of Stokes' theorem. Stokes' theorem tells us how circulation is related to curl. Stokes said this. It said, hey, if I want to calculate this line integral of the velocity, in this case it's the circulation, then I don't have to actually go along that line. I can just calculate how much stuff is in this area. Okay. And for irrotational flows, you have this being 0 because you don't have any curl. And for irrotational flows too, if u is equal to del phi, this would be phi of b minus phi of b. Imagine I've got like some, I'm integrating around this curve. I've got this point x equals b, and I'm going around it. Well, I'm basically taking my phi, which has information on u, and going back to the starting place. And that's why this is equal to 0 too. Okay. So that's a big picture of why we talk about circulation, because we care about airplanes, and why for irrotational flows, velocity has a potential. So all the information in the potential is going to be how we're going to solve things. All right.
But
Yeah.
irrotational flows don't have to be inviscid.
No. But if they are, then it's useful because then whatever potentials you can find they are valid for all time. Because you don't have. Kelvin said, hey, Kelvin said if you're basically viscosity 0, then your amount of whatever circulation you have is just fixed. It's not increasing. But in real flows in reality, like if you have a real airplane wing, it's got boundary layers and this thing called boundary layer shedding and entrainment, then you can get more circulation. But we're not going to be solving that stuff. Okay. So this is where, so that's kind of like the big picture. Last time we talked about we were ending with basically this irrotational vortex. Today, I want to talk a little bit about unsteady irrotational flows. I think if anyone are going to do like the ducts or whatever, or water waves, you'll need to know this. And then we're going to talk about added mass and the complex potentials. All right. So unsteady and viscid flows is also important for understanding added mass. Added mass occurs once you have a body accelerating. And this, I would say this is squarely beyond most undergrad fluid mechanics courses. Most undergrad fluid mechanics courses, when they do these velocity potentials, they consider them steady state. In unsteady, Navier-Stokes equations tells us we keep this unsteady term. And we've already known that we can write the convective acceleration as in terms of the kinetic energy and the vorticity. All right. Where psi is the body force. All right. This is a Navier-Stokes equation. Yeah, I just put the body force on the right. Okay. Navier-Stokes equations for inviscid flows. Of course it's inviscid because I don't have the viscosity. All right. So if it's irrotational, so if there's no viscosity, no vorticity, we can write u as the gradient of some phi. Here, I'm going to use a notation. I put the underline under the gradient, which means that you put in, like a little box, you put in the scalar function, you output a vector. For irrotational flows, you got the following two things are true. This is how we define. So this is very similar to the Bernoulli derivation that I had before, except I keep the time derivative. Otherwise, this is identical. Plus p plus sigma. So this is called the time-dependent Bernoulli equation. All right. So if the gradient of this is equal to 0, that means the thing in the parentheses is equal to a constant that doesn't depend on, that's only depending on time, not on space. All right. So spatial gradient of this thing is equal to 0. That means everything on the right, everything here is a function of time. Only a function of time. All right. I don't really have time. To talk about water waves would require a whole 2 lectures. So let me just give you kind of a big summary. I don't want to go into the entire thing. But if you were to study water waves, you would solve the time-dependent Bernoulli equation. Water waves. So water waves basically would have z is equal to negative h down here. And then the unperturbed surface of water would be called z equals 0. But of course, once you start putting energy into it, it's going to start changing shape. Okay. Then this would be x and y. X and y. This water surface would be called z is equal to eta of x comma t. Let's say it's a 2D wave. Inside the fluid, you'll be solving the Laplace equation, conservation of mass. Okay. And you have basically a normal vector here. And we had to draw that. You draw that normal vector because you would actually consider the curvature, the surface tension forces, which is the normal stress balance. Normal vector for a surface that looks like this, 2D kind of surface, would be the following. X comma 1 over x squared plus 1. Okay. And then to figure out how much curvature force, you take the divergence of this, which I'm just going to tell you what this is. If you take my capillary class, we would go into this in more detail. So this be, for more detail, take capillarity, fluids, and that's spring 2024. Wait, no, that's next year, 25. Sorry.
Question?
Yeah.
What is that something to the n, the abnormal vector?
This
Yeah,
this part?
what is that underneath it?
Oh, it's an arrow.
Oh, that's an, okay.
All right. So basically, figuring out you have to deduce a solution for phi. The boundary. So the governing equation is this. Governing equation is conservation of mass, which is conservation of mass. Yeah, I think we know that. And the boundary conditions here would be that basically there's no normal velocity at the water surface. Oh, sorry. At the ground, there's no penetration velocity into the ground. Okay. Then you have what's called the kinetic boundary condition. This is called the kinematic boundary condition. It relates two functions. One, which is kind of like the shape of the water surface, eta, and the other one is the velocity field. and just says they match on the water surface. Okay. Basically, you can simplify this to be the following. You basically have d eta dt plus d eta dx times d. This is d phi dz. Okay, that's the kinematic boundary condition when you use eta and phi.
D phi z at the end?
Yeah, because that's the vertical velocity.
Gotcha.
All right. There's one more condition. So 1, 2, 3. Third condition is the dynamic boundary condition. This is the time-dependent Bernoulli equation. This says rho d phi dt plus 1/2 rho del phi squared plus rho g eta. That's the height of the water surface plus that's equal to some function of time. Sorry, one more term here, PS, which is the pressure due to the surface tension. Where PS is equal to whatever the ambient pressure is plus the increase in pressure that you get from the curvature. And what we derive above, this was just the following. Was, eta x squared to the 3/2. Yeah, what's up, Layla?
For number 2, where did you get the d eta dx, d eta dx?
Okay, so in 3D, this d by dt is d by dt plus u dot del. Okay, and in two, this is like 2 dimensions. You have this d by dt, and basically you're gonna have plus u times d by dx. Okay, because there's no direction in the other direction. And that's the horizontal. This would be the horizontal velocity. And here, in this case, the horizontal velocity, this u, actually this should be d phi dx. Sorry. All right. Okay, so those are the 3 boundary conditions. Basically, when people solve this, they consider small amplitude waves and linearize. And then they linearize. In other words, you seek solutions that look like this. You seek the water surface that looks like basically this hat symbol means it's going to be just like a magnitude that tells you how tall the water waves are. And they consider these things called traveling waves. If any of you are physics majors, I think traveling waves like occur all the time with like electromagnetism and light and everything else. And basically, if you assume the water surface is going to look like a traveling wave, so why do we call it a traveling wave? We call it that because if you consider this x minus ct, if you were to follow the wave, like surf the wave, for things to look similar around you, you'd have to move at a constant velocity. You'd have to have x going as proportional to t. And then if you do that, everything around you kind of looks the same. This is using the Euler notation. Remember, this is e to the I z is equal to cosine. Let's call that square. Cosine this plus I sine this. Okay. So if you take that, you sub into del squared phi is equal to 0. You're going to get basically phi hat zz minus k squared phi hat is equal to 0. And to make a long story short, what they find is that if you, the boundary conditions, you imagine you sub each of these solutions into that boundary condition, you're going to get a dispersion relation. Boundary gives you dispersion relation. Specifically, that the velocity squared, you can imagine the boundary condition has derivatives of time and derivatives of space. And basically, for that to hold, when you put it all together, you're going to get this. C squared is equal to G over K plus sigma K over rho inverse tanh of KH. All right. Where C is called the phase speed. It's kind of like the speed of a wave. And this is called a dispersion relation because it gives you basically the speed of your rate the speed of your wave, how fast the wave is going, in terms of how long the wave is. Remember, if you have a wave, we have this definition. You have this wave. Let me see. I got to draw this carefully. This is the wavelength lambda, and we say k is equal to 2 pi over lambda. Okay, k, we call k the wave number. It tells you how many waves you have in a fixed segment in a unit length, and this says that basically your Bernoulli. You can imagine your Bernoulli equation, the time-dependent Bernoulli equation. We had basically a gravitational term, but then we also had the pressure term, and these two are kind of like a compromise. Like when basically you have longer waves, this contribution to the speed gets smaller, but this contribution to the speed gets bigger. This has a couple consequences. So, for example, for I'll write it down here. So if you're at shallow water, that means shallow water means that KH is less than 1. So your waves are way, way longer than the depth of your water. Then you can show that C is equal to square root of G. H this is independent of K. And that's why you can only surf in shallow water. Like if you look at those people that are surfing, they only surf close to land. Because if you're trying to surf a wave and that wave's getting faster and faster, you're probably going to fall off your surfboard. For deep water, KH is bigger than 1. C is equal to square root of G over K. Okay. That means long waves travel faster. So imagine you drop a stone in a pond. You drop a stone in a pond, basically the waves, they don't go out kind of like uniformly. They kind of like go farther. They go at different distances depending on how long the wave is. You also have the consequence. Let me draw you what C looks like. So let's draw it in terms of lambda, 2 pi over k, and this would be C. So the speed of your wave. And we said it basically is a sum of an inverse plus a linear term. So it's going to look like this. This zone is capillary waves, waves for which surface tension is important. This zone is deep gravity waves, a deep fluid, and this is shallow gravity. This is where you want to surf. And there's this minimum here, C minimum. It's 4g sigma over rho to the 1/2 power, which I think is around 23 centimeters per second. So basically, if you want to actually generate waves, you have to be, in steady state theory, you have to be at least as fast as this. There's no such thing as a like if you have a duck that's traveling at constant speed, if it travels slower than this, you don't actually hear the duck coming because it won't generate waves. And those waves are because of the basically this. You have gravity trying to keep the water flat, and you have surface tension. Basically, if you've got little bulges in the fluid, it wants to flatten those two. So those two kind of compete, and every time you got a fluid that's pushed down, it wants to go back up, and you basically get energy storage, and it goes to infinity. All right, so that's all we'll talk about water waves. But those of you that are going to do a course project on that, just know that you are solving potential flow, but you're solving the time-dependent Bernoulli equation. You're solving, you're basically solving this time-dependent Bernoulli equation. And this basically what leads to those two things are basically this spatial gradient here and this time derivative here, and also this spatial derivative due with the water surface. All those three together conspire to give you the dispersion relation. Okay, so this idea of looking at the fluid and how energy goes through a fluid, that's important for understanding this paradox. I don't think this one has a name. So we're going to be talking about added mass to understand. And added mass is related to this time-dependent Bernoulli equation, because if you've got a body accelerating, then it's changing velocity as a function of time. Understand this paradox. Okay. So release a bubble from rest. What is initial acceleration? Not a steady state speed. The steady state speed is dictated by a steady state problem with drag and buoyancy. But let's just call it acceleration. So we have this bubble. Gravity's going down. You got a density of the fluid out here, density of the bubble in here, and it's going up initially. Okay. So the force balance you got rho b of the bubble, volume of the bubble, times its acceleration, which we call v dot. So this is basically ma for Newton's law. Is equal to the sum of the two forces. What are the forces acting on this bubble?
Gravity and surface tension?
Yeah, definitely gravity. We kind of care about the interaction of the bubble with the surroundings. You're right, the surface tension dictates its shape. But it's gravity pulling it down. So let's write that first. So this is called...
buoyant force.
Yeah, so this will be the weight. And the buoyant force, which you derived in one of the homeworks, Archimedes' law tells you that, I've got all this heavy, remember this rho b, rho b is equal to 10 to the negative 3 of rho. It's like, it's really, really light. But basically, for me to put that bubble there, you can imagine really far away in the bathtub, the water rose some height. And buoyancy force is the fact that you cause that water to rise, and that water wants to fall again. So the fluid displaced still wants to fall, and we call that buoyancy. And you derived last time that that is proportional to the volume of the bubble. All right. So people usually write this right-hand side they call this the net weight. Okay, rho b minus rho. And we can also write the acceleration, because the volume of these things all cancel, as the following of rho b. So everyone just kind of gets an order of magnitude estimate, and there's also a g over here. So order of magnitude, if rho b is 10 to the negative 3, kind of if you substitute it in, you got basically 0 minus basically, so in CGS units, let's see, rho is equal to 1 gram per centimeter cubed, and then rho b is going to be 1/1000 of that. So you're going to get basically 10 to the negative 3 minus 1 over 10 to the negative 3 times g. So that basically is going to give you around 10 to the 3 g. So this tells you that basically the bubble should rise at 1,000 times gravity. In other words, in 1 second, it will travel a distance of 1/2 10 to the thirds times gt squared, which is about 10 kilometers. So that's way too fast. That's way too fast by like that's 3 orders of magnitude. I release a bubble underwater. This says that the acceleration of the bubble is actually independent of the volume. So I release like, a champagne bubble, beer bubble, the dolphin bubble, and it's going to travel. It shouldn't travel very far. It'd travel, you can imagine it on the order of like the size of the bubble. But here it says it's basically going to like shoot through the water surface. Physically, why is it so accelerating so fast? The reason it's accelerating so fast is the bubble weighs almost nothing. It weighs like 1,000 times less than all the fluid around it. So that fluid around it is like shooting it like a gun. It's super, super fast because F equals ma. This m is pretty much 0. It's just super, super lightweight. So this is a big issue. It means that based on Archimedes' law, you can't predict acceleration. So physically, the reason why we are so wrong with this calculation is because you imagine the streamlines of what's going on. I won't mess up that, but basically as this bubble is rising, I'll draw a little hole for where the bubble was in the past. Here it was filled with air, and then it becomes filled with water. So you imagine for this thing to rise, I need water to go into this spot. So water fills spot of where bubble was. And it's not just filling it at some speed, it's accelerating into it. So that means for us to calculate how quickly the bubble accelerates, even the bubble's air, you need to calculate how quickly water accelerates, because water is going into the wake. And that's this whole principle of added mass. We call it added mass because when you just consider the bubble mass, you get an incorrect value. So in some ways, this is added mass is the mass of the fluid around it due to acceleration of surrounding fluid. That's the big concept. In aerodynamics, like a lot of these, there's this thing called a bumblebee paradox. I think Rayner, he's a pretty famous aerodynamics person. They actually try to use steady-state airfoil theory, the drag and lift goes as the velocity squared. And they said that bumblebees can't fly. And of course, that's a paradox because they do fly. But basically, they had to consider these accelerative effects of the wings going up and down. Okay, that's it for today. The calculation of added mass involves us integrating the velocity in a fluid. and figuring out basically using these ideas of the potential. So we're going to do added mass. Probably do added mass this week. On Wednesday, we'll try to get into the D'Alembert's paradox, the integration of the force around the boundary. And I think by the end of next week, you'll have finished the complex potentials, because we're also going to have the quiz next week. All right. So we got about 3 weeks left before holiday break and then the course projects, which I think are going to start after Thanksgiving. So if you have any questions on your course projects, you can. I think I gave feedback to most of you. I have a pretty good idea of you basically want to show something that's kind of like fun, but you want to have some substance there too. So if you have like a demo or some videos, that'll be nice. But you don't want to just go there and do like math for 30 minutes. You want to have something physical people can take away too. So I try to give you some suggestions to do that.